Friday, we went a little further with the Bohr model of the atom than we had on Thursday. We showed you these three diagrams. And the first diagram, if you remember, we said was a reference diagram. We called it diagram number one. It was the spectrum that was produced when we had a hot solid or a hot liquid or a hot gas under high pressure generating EMR. Now, you learned on Friday that that generates every frequency of EMR, particularly visible light. When we look at this hot glowing solid, hot glowing liquid, or hot glass under high pressure, it would look like just white light. It would look like what we see when we look at the light bulb or when we look at the sun, white light or yellowish light. But when we put that through a prism or a diffraction grating, it's going to split it up. But because it's actually all the colors of the rainbow, all frequencies, not just very specific frequencies, then what we're going to get on the screen in this spectrometer is a continuous spectrum, a rainbow. Okay, on Friday night, I went outside. We had a beautiful full rainbow across the east side of Okotoks. That was dispersion, right? That was all the colors of white light going through effectively a prism, which was the Earth's atmosphere, the damp Earth's atmosphere, and it was splitting up into all the colors of the rainbow, a continuous spectrum. Yeah, that's not the Bohr model of the atom per se, but we need to reference the Bohr model of the atom against that diagram of the continuous spectrum here. Okay, so let's look at diagram number two now, which is when we have a hot gas, but notice it's a hot gas under low pressure as opposed to high pressure. This hot gas under low pressure also generates what appears to be white light. Okay, if you look up at the ceiling right now, and you look at these fluorescent light bulbs, that's what we're getting. These fluorescent light bulbs appear to be white light. But if you looked at it through a prism or diffraction grating, then it's going to split that white light, that so-called white light, up into its components, which is not all the colors. It's not a continuous spectrum because that light is generated in a different way. That's generated by electrons making transitions from high levels to low levels. So what we see there is a combination of different colors, just not all the colors. It's a combination of, in this case, red and orange and green and blue and indigo and violet that appears to be white when it's mixed together, but when we separate it, looks quite a bit different than the continuous spectrum that also appeared to be white. Now, if we go to diagram number three, we're back to our first diagram, our reference diagram, but we also have a cold gas in the mix there. When we have a cold gas, all that's going to do is change a continuous spectrum into what we call an absorption spectrum, because that cold gas absorbs certain photons, certain frequencies of EMR, causing electrons to jump to higher levels. So the electrons jump to a higher level, there's a photon missing. So therefore, you're not going to get a continuous spectrum. You're going to get a continuous spectrum minus the photon that was absorbed. Okay, another electron makes another transition upwards to a higher level, then you're going to be missing another photon from that continuous spectrum on the right-hand side. There is a question on your unit test, I'm telling you right now, where you have to remember this stuff. Here's the way I would do it. Okay, for me, this is what works. Okay, if something different works for you, then that's great. But here's what works for me. Okay, I try to ingrain this picture, these three diagrams in my mind. So I visualize them. I can see in my mind with my eyes closed a continuous spectrum. Sometimes we call this a line emission spectrum. Sometimes we just call it an emission spectrum. An absorption spectrum. I see them in my mind. And then I just remember hot gas, low pressure, cold gas. That's all I got to remember. Hot gas, low pressure, cold gas. And then if I get a diagram that looks like one of those, I associate it with hot gas, low pressure, cold gas, or the one that I didn't memorize, which is anything else, and it's the top one, right? Or if I see a question that says, I think like you did in your unit assignment, I think in your unit assignment it said, when it passes through a cold gas, if I remember that there's a cold gas in the third diagram, I don't have to remember that it's an absorption spectrum. I just see the diagram in my mind, and then I say, oh, yeah, that's an absorption spectrum because it's a continuous spectrum minus those photons. However you remember it, okay, you're going to get one on your unit test. I think you got one on your unit assignment, and on your practice question set, you're going to get one on your unit test on Wednesday as well. All right, today what I want to do with the Bohr model of the atom is go just a little bit further and talk about what we call electron level diagrams. You guys have a copy of this electron level diagram for you already? Photocopied for you? Looks like this. It's on the back of the page that had the example questions on transmutation. So here's the front of the page. Here's the back of the page. This electron level diagram shows different energy levels that electrons can be in the hydrogen atom. Keep in mind that we could draw a similar diagram for any other element, not just hydrogen, just the numbers would be different on it, that's all. Shows the levels they can be on, but it also shows the transitions that these electrons can make. In addition, it shows the energy of each level, and from that we can get the energy of each transition that it can make. Notice that we say that if an electron is not on the ground state, we say it's in an excited state. The ground state is a state that's closest to the nucleus of the atom. And that's where the electrons want to be. Just like when I go to a hockey game, I want to be down by the ice level, in the lower level. But if I'm not in that lower level, the ground state, then I'm going to be in an excited state, level 2, level 3, level 4. Now, a couple things that I want you to notice about this. The numbers on the left-hand side correspond to the energy of each level. Notice that they're all negative. Also notice that these numbers get bigger as I approach the nucleus. And finally, also notice that the difference between each of these energies, and therefore each of these levels, gets bigger as I get closer and closer to the nucleus. So the spacing is not even. Doesn't matter whether you're talking about hydrogen or any other atom, the numbers will be different, but the spacing will look pretty much the same as this. Each of these lines corresponds to a different transition that can be made within the atom. And of course, we could also go the other way. Instead of from level 2 to level 1, we go level 1 to level 2. Or instead of level 2 to level 6, we could go level 6 to level 2, we could go level 2 to level 6. And finally, we could label a 7th level, an 8th level, a 9th level. We just ran out of space. They get closer and closer together, so at some point we just physically run out of space to do it. Okay, so what do you got to do to analyze a problem involving one of these electron level diagrams? Well, it doesn't matter what you're asked to find. Doesn't matter what you're asked to find. You're going to subtract two energies. And then you might do something after that, or you might just leave it at that. Let's take a look at the first example that we have on that sheet that I handed to you last week. Example number 1, it says, how much energy is emitted when an electron makes a transition from the 3rd level to the 1st level in hydrogen? Hydrogen is what we have the diagram for, so that's good. How much energy is emitted when we go from level 3 to level 1? Don't ever use just 1.51 or 13.6, ever. There is nothing you will do in Physics 30 where you care about the energy of one specific level, ever. You will always use the difference between two numbers, the difference between two levels. So in this question, we are asked to find the energy emitted when it goes from the 3rd to the 1st. What we're going to do is subtract 1 from 3. The energy of this transition is the final energy, level 1, minus the initial energy, level 3, which gives us negative 13.6 EVs, minus negative 1.51 EVs, which gives me negative 12.09 EVs. The energy emitted when we go from 3 to 1 is 12.09 EVs. It'll always work out to be positive if it's emitted and negative if it's absorbed. But I wouldn't worry about the negative sign there. If you said 12.09 EVs, you'd be okay there. All right? That's easy enough, right? Didn't use this one, didn't use this one, use both of them combined. That's always what we're going to do. Take a look at number 2. 2 says an electron on the 1st level absorbs 12 EVs. To what energy level does the electron raise? Now, it doesn't say where it gets that energy from. A photon or the kinetic energy of another electron or electrical energy. Listen, it doesn't really matter. So on the 1st level, it absorbs 12 EVs. Where does it go to? So on the 1st level, it absorbs 12 EVs. Well, 12 EVs would take me to What, negative 1.6? So tell me, which level is it going to go to, number 2 or number 3? Which one is it? No, it's not 3. It's going to go to 2. You only had 12 EVs available to you. You needed 12.09 to get from 1 to 3. Okay, if I take my son to buy something at the store and he needs $100 to buy it, but he only has $98, he can't buy the $100 toy. He can buy the $60 toy. He can settle for the $60 toy, but he can't buy the $100 toy. He is oh so close to being able to afford the $100 toy. But unless he has $100, they're not going to give him the $100 toy. Now, you could argue that maybe his dad should lend him $2, but I'm cheap, so I'm not gonna. He can't buy the $100 toy. Okay, here we can buy the $3.40 toy. Okay, we can't buy this one because we don't have enough energy to get there. Okay, even though we're oh so close. We got 98 of $100, but we're not there. So what we have to do is settle for something a little bit lower. We can go to the second level. Now, be careful, because if an electron absorbs a photon, it's actually got to absorb the right amount. So it would either absorb what would this be, 10.2 EVs to go to level 2, or it would have to absorb 12.09 EVs to go to level 3. It wouldn't absorb a photon of 12 EVs. It just wouldn't do it. But if you have some other source of energy, then it can take part of the energy and go to the lower of the 2 levels. Make sense? You're never going to go to the 3rd level unless you get 12.09 though. 12.08, nope. Okay, doesn't go. Okay, it's like my son having $99.94. I'm not gonna give it to him. Okay. Yeah, it'd have to be a really nice cashier though. Nicer than his dad, right? Example number 3. How much energy needs to be absorbed when an electron makes a transition from 2nd to 4th? And then what's the frequency and wavelength of the EMR that needs to be absorbed? 2nd to 4th. Well, the energy difference is going to be what? Negative 0.85 minus negative 3.4. Don't forget the minus negative. That's going to give me 2.55 EVs. Now, if I want to find the frequency, all I'm going to do is say E is equal to H times F. And if I want to find the wavelength, I'm going to say E is equal to HC over lambda, or lambda is equal to HC over E. Yeah, I'm not sure what we get there for numbers, but pretty easy to figure out at this point, right? Make sure you use the right Planck's constant. If you're unsure of whether you should use joules or electron volts, just convert all this to joules, and then use the 6.63 value. There would be no issue, though, with using electron volts in this question if you wanted to. This is something times 10 to the 14. I think it's 6 point something times 10 to the 14. Which makes it visible light, and this is something times 10 to the minus 7 meters. And finally, the last question, question number 4, says, what's the ionization energy for an electron on the 1st level of the hydrogen atom? The ionization energy, what does that mean? Yeah, it's the energy required to completely remove it. All right, so let's figure that out. We want to go from level 1 to level infinite. The energy required to remove that would be 0 minus negative 13.6, which is just 13.6 EVs. All right? Be careful now. There's a danger when we see that answer of saying, oh, there, all I have to do is read one number. You told us to never just read one number, always subtract, right? Yeah, I'm telling you that, always subtract. That's not 13.6 because this number per se is 13.6. It's 13.6 because 0 minus negative 13.6 is 13.6. So it's still taking 2 levels and subtracting them. You will always do that, always subtract. And then maybe after that, set it equal to HF or HC over lambda or something like that. There is worksheet number 26 that goes along with this. I believe it's only 3 questions. I'm not going to formally assign that for homework, but I'm going to suggest that you do 1 or 2 or 3 of those questions if you have time tonight so that you can ask me tomorrow about it. Bottom line is, if you can do what we just did, you're fine. You're okay with this. And it's not crazy hard, but if you do feel like you need a little bit of practice, then take a look at that worksheet and just ask me a question about it tomorrow or Wednesday morning.